Today we're going to be talking about the total response of first order circuits. And spelled circuits again. The first thing that we are going to do is actually review what we talked about last Friday, just very, very briefly, right? So on last Friday, we had natural response circuits that look something like this. So I think we started off with a RL circuit, if memory serves me correctly. Here's R, here's L. And what we found was that any voltage or current signal in this circuit could be expressed using the following mathematical function. Y of t, representative of any current or voltage, would be equal to y at 0 minus for t less than 0 minus, and y at 0 plus e to the negative r over lt for t greater than or equal to 0 plus. And then we also talked about RC circuits, which would have been something like this. Switch opening at t is equal to 0. And we found that y of t will always be of the form y at 0 minus for t less than 0 minus, and then y at 0 plus e to the negative t over RC for t greater than or equal to 0 plus. So we're going to look at these equations here in a moment, but one of the things that I want to point out is that in our natural response problems, we are always disconnecting our voltage or current source from influencing the behavior of our energy storage element, right? So it doesn't have to physically be disconnected like we have here. We also worked examples where there was a short circuit that was effectively isolating the energy storage element from the source and things like that. So effectively, any circuit where the source is taken out is going to be a natural response circuit. And in a little bit, when we look at total response circuits, that's any circuit where a source is left in. So always connected to, or winds up being connected to, the energy storage element at t is equal to infinity. But before we get to that point, I want us to look at these two equations because they are effectively the same thing, except for what's being multiplied by time in that exponential function there. So because these are literally the exact same relationship, electrical engineers have given that rate of decay a special name, and it's called the time constant. So time constant is defined as the amount of time it takes for a first order circuit's current or voltage . to decay to, I think it's 36.87%. Let me double check that really quickly. $36.78. Transpose those two numbers. Of its initial value. You may be saying to yourself, 36.78% seems like a really weird target to define a time constant to. 36.78% corresponds to e to the minus 1. So effectively, if we have some signal, let's say that this is the amount of time on the left-hand side, and this is the ratio of y of t to y at 0 plus in exactly one time constant. The symbol for a time constant is tau. Y of t over y at 0 plus is going to be exactly equal to e to the minus 1, which is 36.78%. In two time constants, we'll have e to the minus 2, which is 13.53%. In three time constants, that ratio will be e to the minus 3. Which is 4.98%. In four time constants, that ratio is going to look like e to the minus 4. Or 1.83%. And in five time constants, we're going to have e to the minus 5, which is 0.67%. So the reason why I'm mentioning this is because we talked about the concept of t equals infinity being a long time after our transient signal has died out. Well, for the intents and purposes of engineers, infinity is just 5 time constants. If we allow something to discharge to where it's less than 1% of its original value, we say that it's effectively fully discharged. So infinity, in the perspective of these transient analysis problems, really just means anytime more than 5 time constants, we're back at a DC steady state. And we'll use that if we have a chance to do the lab for this material. So based on our definition of a time constant, we can pretty easily see that the time constant for an RL circuit is simply the ratio of L divided by R. Because if we plug in T is equal to tau here, we would have negative R over L times L over R, which is going to be exactly e to the negative 1, right? So that's one time constant for an RL circuit. And then our time constant tau is simply R times C for RC circuits. Okay. So I hope it's pretty obvious, but the units of a time constant are in seconds because it's an amount of time that elapses for the signal to decay to some specific value. We can see that pretty easily. So we have inductance, which is in henries or volt seconds per ampere. divided by resistance, which is measured in volts per amp. So the volts cancel, the amps cancel, and are left with seconds in the numerator, right? So time constant is measured in seconds. Looking at the time constant for RC circuits, we have resistance, which is volts per amp, multiplied by capacitance, which is measured in farads or an amp second per volt. Once again, the amps cancel, the volts cancel, and all we're left with is seconds. So a time constant is always measured in seconds, and it's because it's the amount of time that has elapsed until the signal has decayed down to 36.78% of its initial value. So now, instead of having completely separate equations for RL circuits and RC circuits, we can have a single equation. Y of t is equal to y at 0 minus for t less than 0 minus, and y at 0 plus, e to the minus t over tau for t greater than or equal to 0 plus. And our step 4, that is an R, in our analysis process is no longer find REQ and find LEQ during the transient condition. It is find the time constant. During the transient condition using these equations, so that it's literally now the exact same process regardless of what type of circuit we're analyzing. All right, so because this is the natural response and we're about to talk about the total response, I'm going to make an extremely small modification to that equation that I just gave you. I'm literally going to put y sub n there to denote that that is the natural response. Our total response is simply the sum of the natural response plus the forced response of the system. And the forced response of the system is nothing more than whatever the system is being forced to do due to the presence of some sort of excitation source, meaning a voltage source or a current source or some combination thereof. Okay. So if we were to look at the following circuit, let's make this the easy RC circuit that we were looking at before. And now our switch is going to be closing at t is equal to 0. Let's talk about what's going to happen. Let's say, just for the sake of argument, that the only thing we're interested in is our capacitor voltage as a function of time. So at t is equal to 0 minus, what should our capacitor voltage be? But t is equal to 0 minus, our switch is an open circuit. So this should be pretty easy to figure out. What should the value of the voltage drop across the capacitor be if the voltage source was never connected to the capacitor? 0 volts. At t is equal to 0 plus, what does the voltage drop across the capacitor have to be? Disagree. Voltage drop across a capacitor cannot change abruptly. So if it was 0 volts at 0 minus, it has to continue being 0 volts at 0 plus. At t is equal to infinity. What will the voltage drop across the capacitor be, Camden? Vs. So effectively, what we are seeing, or what we're trying to figure out what's going on, is how this capacitor is going to charge up. So everything that we did on Friday's class was about how energy storage elements discharge effectively. And what we're talking about away is how they charge. And it is related to how they discharge, which should make sense. So this quantity Vc at infinity, this is the forced response. Okay. So we should be able to see that y of t is, once again, our natural response plus our forced response. So I'm going to put something here. I'm just making you aware of this right now. This technically has an error in it that we are going to fix, so maybe don't write stuff down until after we fix it. We're going to have y at 0 minus for t less than 0 minus. And then we're going to have y at 0 plus e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So if we were dealing with our capacitor voltage, we find that there's a little bit of a hiccup here, right? So our capacitor voltage as a function of time would look like 0 volts for t less than 0. And then it would look like 0 volts e to the negative t over tau plus Vs for t greater than or equal to 0 plus. What's our problem? Yeah, so effectively it looks like our capacitor voltage instantly changes from 0 volts to Vs the moment the switch changes states, which we know literally can't be true because that would require an infinite amount of current to make that happen. So what we're going to do is we're going to make a little modification that's just going to fix that discontinuity. Instead of having just y at 0 plus, instead, we're going to have y at 0 plus minus y at infinity. So that's going to correct things to make this a continuous function in time. So that would make this look like negative Vs e to the negative t over tau plus Vs. And so we would see that at t is equal to 0 plus, the voltage is 0, and then it is going to gradually increase up to Vs once that exponential portion dies out. That is total response. So now let's work a couple of example problems. So let's pull some old ones from some tests. Let's see what I was doing in the spring of 2020. Oh, spring of 2020 was COVID. All the tests were online. That's not going to help. All 2022. Well, that folder is somehow just empty. All right. Geez Louise. All right. Fall 2019. says exam 2 images, but not the exams itself.
What do you draw this?
LaTeX. All right, so here's something. So let's say that we are going to analyze this circuit and we are going to try to determine what Vx of t is and what IL of t is, okay, using our process here. So the first thing is that I can definitely see that this is a total response problem because that 2 amp source and that 10-volt source, they're not in any way, shape, or form touching the switch. So they're always in the circuit, which means they're always going to influence the behavior of what's going on with the inductor. So there is going to be some non-zero force response that I'm going to have to take into account. So this is definitely a total response problem, right? So our first step for this particular circuit would be the exact same thing as we've been doing. We're going to analyze our circuit at t is equal to 0 minus and figure out what's going on. So at t is equal to 0 minus, our switch is an open circuit and our inductor looks like a short circuit, okay? So because our switch is an open circuit, this part of the circuit literally doesn't do anything at all because it's disconnected. So I'm going to choose just not to draw it just for the sake of not having to draw stuff that's not doing anything. So here is our 10-volt source on the bottom left. Here's our 5 ohm resistor across which we have Vx at 0 minus. Here's our 5 ohm resistor on top. $15 ohms goes here. 10 ohms. 2 amps. 6 ohms. And the current flowing down through this path is IL at 0 minus. So how might we go about solving for either of those quantities? Brennan, you have any thoughts? So we can't use current division as things presently are because there's that voltage source that's messing things up, right? If the voltage source weren't there, we could definitely use current division to find the current flowing through the branch containing the 15 ohm resistor in series with the 6 ohm resistor, as well as the branch containing the two 5 ohm resistors in series. Which if we were going to use superposition would give us kind of half of what's going on. Superposition actually wouldn't be terribly bad here. I would probably be lazy enough to just use mesh because that way I wouldn't have to analyze the circuit twice, but superposition would allow us to do this using current division and voltage division, which wouldn't be hard. It's just analyzing the circuit twice, and I'm feeling really lazy because I don't feel great. So let's go with mesh. So this is will be our mesh current I1. This will be our mesh current I2. Hopefully right from the jump, we can see that I2 is simply negative 2 amps. Everybody okay with that? And now I'm going to write a KVL equation around mesh 1. So that should look like negative 10 volts plus 5 ohms I1 plus another 5 ohms I1 plus 15 ohms I1 minus I2 plus 6 ohms I1 minus I2 is equal to 0. And those are my two equations. So let's solve this bad boy. Two equation, two unknown systems. So the coefficient for I1 in my first equation is 0. The coefficient for I2 in my first equation is positive 1. And then my constant term is negative 2. In my second equation, my coefficient for I1 is going to be 5 plus 5 plus 15 plus 6. So that is 31. My coefficient for I2 is negative 15 minus 6. So that's negative 21. And then my constant term is 10 volts. So solving, I get I1 is negative 32 over 31 amps. And I2 should be negative 2 amps. So using this information, what would be Vx at 0 minus be? I1 times 5 ohms? Anything you want to correct? Negative I1 times 5 ohms. Why is it negative, Camden? That's exactly right. So Vx at 0 minus is negative I1 times 5 ohms. So that will be 32 over 31 times 5, 160 over 31 volts. And IL at 0 minus would be what? I1 minus I2. Which comes out to be positive 30 over 31 amps. Anybody have any questions regarding our analysis at t is equal to 0 minus? Fairly straightforward. All right, because this paper thing doesn't have a whole hell of a lot of room, I'm just going to write up here Vx at 0 minus we found to be 160 over 31. IL at 0 minus we found to be positive 30 over 31. And now I'm going to erase some stuff. So at t is equal to 0 plus, now this 9-volt source, positive polarity on bottom, and 27 ohm resistor are effectively being switched in to the circuit. So they should be in here now. So here's my 27 ohm resistor. And then here is my 9-volt source like so. Let's see, my 6 ohm resistor is going to need to be moved up a smidge. And then IL was direction down. So I'm going to put a current source direction down. That is 30 over 31 amps, like so, representing IL at 0 plus. Erase all this work. So while I'm erasing all this stuff, how are we going to figure out what Vx at 0 plus is? Probably still mesh. That seems pretty reasonable. Let me think about some things just really quickly here. So there's one node, here's a second node, here's a third node, here's a fourth node, fifth node. Yeah, mesh is going to be way, way less of a pain in the butt. Yes, sir. Oh, you were right. So let's work it if the arrow is going the other direction. Yep. Still going to be a total response problem. I just misread how the arrow was working. But yeah, you're right. All right, so mesh analysis. I1, I2, and I3. All right, so we can see from the jump that I3 is negative 2 amps and I2, minus I3 is 30 over 31 amps. And so that means that I2 is 30 over 31 plus negative 2, so minus 2. Is negative 32 over 31 amps. So the only thing that we have left to solve for is I1, and we'll get that by writing a KVL equation around mesh 1. So negative 10 volts, I'm going to lump these together. 5 plus 5 looks like 10. I1, and then we're going to have 15 I1 minus I3. And then 27 I1 minus I2 minus 9 volts is equal to 0. I'm going to be wildly lazy and do this as a 3-equation, 3-unknown system. So in my first equation, my coefficient for I1 is 0, my coefficient for I2 is 0, my coefficient for I3 is 1, my constant term is negative 2. In my second equation, my coefficient for I1 is 0, my coefficient for I2 is positive 1, my coefficient for I3 is negative 1, and my constant term is 30 over 31. In my third equation, my coefficient for I1 is 10 plus 15 plus 27, so that's 25 plus 27 is 52. My coefficient for I2 is negative 27. My coefficient for I3 is negative 15. And my constant term is 10 plus 9 is 19. Solving this, I get I1 is negative 1205 over 1612 amps. I2 is the negative 32 over 31 that we already figured out. I3 is negative 2 amps. So we already know what IL at 0 plus is, because IL at 0 plus must be IL at 0 minus, or 30 over 31 amps. So how would we solve for Vx at 0 plus? Yeah, the exact same way we did earlier. Negative 5 ohms times I1. So that is going to be positive 1205 over 1612 times 5 comes out to be 3.738 volts. Not entirely sure why the calculator didn't give it to me in a fraction, but that's fine. So let me write this stuff down. Okay, so before we move on to t is equal to infinity, anybody have any questions about the analysis that we've done here? Fairly straightforward application of mesh analysis, nothing too wild or particularly crazy. Okay, so erase all this jibber jabber. So what's the only change that I'm going to need to make to my circuit that I have drawn over on the left-hand side to account for the fact that we're at t is equal to infinity now? Yep, so my inductor current source should now just be a short circuit, because since we are at DC steady state at t is equal to infinity, our inductor looks like a short circuit. And looks like mesh analysis is probably going to be the best way to solve for Vx and IL for this as well. So let's just leave those mesh currents labeled I1, I2, and I3 and put them into use. So once again, we could see that I3 is negative 2 amps. And now we're going to have to write a KVL equation around mesh 1 as well as mesh 2. So our KVL equation for mesh 1 is negative 10 volts plus 10 ohms times I1 plus 15 ohms times I1 minus I3 plus 27 ohms times I1 minus I2 minus 9 volts is equal to 0. Around mesh 2, we have 9 volts plus 27 ohms I2 minus I1 plus 6 ohms I2 minus I3 is equal to 0. And those are our three equations that we can solve. So in my first equation, my coefficient for I1 is 0, my coefficient for I2 is 0, my coefficient for I3 is 1, constant term is negative 2. In my second equation, my coefficient for I1 is once again 52. My coefficient for I2 is negative 27. Coefficient for I3, negative 15. Constant term, positive 19. In my third equation, my coefficient for I1 is negative 27. Sorry, stomach pain. My coefficient for I2 is 27 plus 6 is 33. And my coefficient for I3 is negative 6. Constant term is negative 9. Solving, we get I1 is negative 310 over 329. I2 is negative 463 over 329. And I3 is negative 2, much like we would expect. Vx at infinity is going to be negative 5 ohms times I1, as it has been literally every time we've looked at this. Which comes out to be 1,550 over 329. IL at infinity is I2 minus I3. So negative 463 over 329 minus negative 2 comes out to be 195 over 329 amps. Let's write this down. 1550 over 329. Anybody have any questions, comments, or concerns about our analysis at t is equal to infinity? Fairly straightforward stuff. All right, so now we need to figure out our time constant. Remind me how we're going to do that. Yep, absolutely right. So because this is an RL circuit, our time constant is simply LEQ over REQ. And LEQ, I firmly believe, is 2 Henries because it's the only inductor in the circuit. So we don't have to do any work for that. So how do we find REQ? Well, we take our inductor out of the circuit. So that's what this short circuited terminals here are for. And then we need to be looking at a dead network. So that means I'm going to turn off this voltage source. I'm going to turn off this voltage source. And I'm going to open circuit this current source. And we're looking in here. So let's call this A and B. And let's identify our nodes and see how things shake out. All of this stuff down here in pink is node B. Everything here in green is going to be some node. We'll probably call it C in a moment. Here's a node. Here's a node. So A, B, C, D, and E. All right, so here's A on this side, here's B on this side. To go from A to B, I definitely have to go through C. So let's put C right here. This is that 6 ohms of resistance. Now I can go from C to B directly through the 27 ohm resistor. So let's put that guy here. I can also go from C to D to E to B. So here's D and E. So from C to D is the 15. From D to E is a 5. And from E to B is a 5. And so to me, REQ looks like 6 ohms plus 27 in parallel with 25. Anybody have a problem with that? So 987 over 52 ohms. From this, our time constant is LEQ over REQ is going to be 2 henries over 987 over 52 ohms. Looks like 104 over 987 seconds. And the inverse of tau is then 987 over 104 per second. I'm going to write those guys up here. You'll see in just a second. All right. So before I erase all this junk again, anybody have any? Yes, Brandon. What? So that's the question that I believe John just asks, and I will show you in literally just 1 second why the inverse of tau is important. Okay. All right. So any other questions about this before I erase it all? It's a good question. I'll literally will answer in just 1 moment. Any other questions? All right. So the last thing that we need to do is to plug stuff into our generic equation, and this part will explain why the inverse of tau is important. This would erase faster. It would be great. Okay. All right. So our generic equation is y at 0 minus for t less than 0 minus y at 0 plus minus y at infinity e to the minus t over tau plus y at infinity for t greater than or equal to 0 plus. So effectively, the inverse of tau is the coefficient that's multiplied by time in our exponential function, right? Because we have t divided by tau is the exact same thing as t multiplied by the reciprocal of tau. So for us, looking at our inductor current, this is going to look like, so IL at 0 minus was 30 over 31. For t less than 0 minus, then we're going to have 30 over 31 minus 195 over 329 e to the negative 987 over 104 t plus 195 over 329 amps for t greater than or equal to 0 plus. And just for the sake of argument, 30 over 31 minus 195 over 329 comes out to be 0.375 amps. So I'm just going to write this as so. For Vx, we're going to have the voltage at 0 minus, so 160 over 31. Then we have the voltage at 0 plus, which was 3.738. Minus the voltage at infinity, 1550 over 329. e to the minus 987 over 104t plus 1550 over 329 volts for t greater than or equal to 0 plus 3.738 minus 1550 over 329. So that is negative 0.973 there. Action, why are you shaking your head no? Yeah. Apparently this was a test question a few years back. Long, for sure. If you look at the practice exams and all of that kind of stuff, you'll see, well, let's talk about the test because we're effectively done with the material for the exam now. So there's going to be 5 theory questions and all that kind of stuff. So I'm going to ask you about, according to Thevenin's theorem, blah, 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 according to Norton's theorem, blah, 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 those type of questions. Ask you questions about the relationships between current, voltage, power, and energy in both capacitors and inductors. One question that you'll probably see on every one of the practice tests is something like the amount of time it takes a current or voltage signal in a transient analysis circuit to decay to less than 1% of its final value is blank time constants. The answer is 5. We talked about that today. So those are your theory question kind of things. Then for the analysis questions, there's going to be 5 questions regarding Thevenin and Norton equivalent circuits. So there's going to be 3 circuits total. The first circuit will not have any dependent sources in it. And so I'll ask you for either Thevenin voltage, Norton current, or Thevenin resistance, just 2 out of those 3 quantities. Your second problem will be a circuit that contains a dependent source as well as independent sources. And I will ask you for Thevenin voltage and Norton current. And then the last Thevenin problem will be a circuit that only contains a dependent source. So you'll have to use the test source method to determine the Thevenin resistance directly. So that's all the Thevenin and Norton stuff. That's the first 5 questions for the circuit analysis portion. Then I believe there will be between 6 and 8 circuits on capacitors and inductors. So you should expect one problem, like you'll have a graph effectively, and it will either be inductor current or inductor voltage, or capacitor current or capacitor voltage. And then based on the graph, you will have to tell me voltage, power, or energy. Then there will be effectively the exact same type of problem, but instead of giving you a graph, I give you a mathematical function, and I expect you to be able to manipulate that function correctly in order to give me voltage, current, power, or energy. Then there will be one problem probably on either inductor or capacitor combination. Then there will be one problem that is similar in nature to homework set 12, problem 3, or problem 5. Those are 2 homework sets or 2 problems that I really like. So usually a question like one of those shows up on the top. You've been warned. Homework 12, problem set 3, or excuse me, homework 12, problem 3, or problem 5. One of them is a KVL problem, the other one is a KCL problem, and it just has inductors and capacitors in it. So after we get done with the inductor and capacitor problems, then we're in the transient analysis bit. And so there's just going to be 2 circuits, and then each circuit will have either 4 or 5 questions, I believe. So I'll ask you, what's going on at t is equal to 0 minus? What's going on at t is equal to 0 plus? What's going on at t is equal to infinity? Tell me the time constant, put it together. And then the exact same thing for the other one. For the one that you don't need to analyze at t is equal to infinity, I won't ask you to analyze it at t is equal to infinity. So you will know very directly whether or not it's a transient force analysis problem or a total response problem on whether or not I ask you to do a damn thing at infinity. That's the test. That's literally the entire test. I just told you what all 25 questions are. And if you look at any of the practice tests, you will see that that is exactly what all 25 questions are. So, all right. Start working on an in-class assignment. I'm going to see if I can get the lab set up really quickly. All right, I'm ready for the lab if you guys are. So instead of using the function generator, the digital oscilloscope, and all that kind of stuff that we have here around the room, I'm using this old Diligent board, which is how we used to do all of the labs in this class before we bought the new equipment. So first part of the procedure here is using a multimeter. I measured the 1 kilo ohm resistor, and I'm getting 989 ohms. So you should write that down somewhere. Okay. 989 ohms. We're doing the lab. Then our goal is to construct this very simple circuit that contains a resistor in series with a capacitor. Circuit is constructed. All of that kind of good stuff. We're going to be playing around with the oscilloscope. So let me pull up the waveform thing here. So that's not what I wanted to have happen. So if we go over here to the wave generator, we can see that we are running a 200 hertz square wave with an amplitude of 2 volts, which is what we are instructed to do. And then I've come over here to scope 1. And so the yellow curve is effectively my input signal. So that is my square wave. And the blue curve is the voltage drop across my capacitor. And so we can see that it takes time for the blue curve to catch up to the yellow curve because it takes time for the current to change to the capacitor. We know that because of the derivative-based relationship and all of that kind of good stuff. So if we pop back over here to our thing, we are asked to record the maximum value of the voltage and the minimum value of the voltage. And so if we look at this guy right here, it's set to be 500 millivolts per division. And this triangle thing right here is giving us our origin. So we are 1, 2, 3, 4 divisions up. So that's 4 times 500 millivolts or 2 volts. So our maximum value is positive 2 volts. Same thing, 1, 2, 3, 4. Our minimum value is negative 2 volts. So the voltage drop across the capacitor should have a functional form based on exactly what we did in class today. And so I'm expecting you guys to be able to determine what coefficients A and B are. So A is just y at 0 plus minus y at infinity. And then B is just y at infinity. So if we go back here and we look at this screen, we effectively need to decide whether we're going to look at a charge cycle or a discharge cycle for this capacitor. So I say we look at this charge cycle that's over here on the right. Okay? So at t is equal to 0 minus would be this vertical line right here. Can you guys see my mouse and all that kind of stuff moving? So that's t is equal to 0. And then way over here to the right is effectively t is equal to infinity. So our voltage at 0 is negative 2 volts. Our voltage at t is equal to infinity is positive 2 volts. So our coefficient A is negative 2 minus 2 is negative 4. Okay. And then our coefficient B is just the voltage at infinity, which is positive 2. So using A is equal to negative 4 volts and B is equal to positive 2 volts, literally plug those numbers in and tell me what you should get right here. So negative 4 e to the minus 1 plus 2. Hannah, what'd you get? Okay. Somebody else, what'd you get? 0.528. So after one time constant has elapsed, our voltage should be about 528 millivolts, okay? So now what we're going to do is effectively move our cursors and all of this kind of stuff to kind of seek that out. And so this is going to take me a moment to remember how to do this because I haven't used this stuff in forever. So I'm putting one cursor here at effectively t is equal to 0. And then I want channel 2 to be at 528 millivolts. Okay. So right now, at this point, channel 2 is, because there's a little bit of noise, about 524 to 528 millivolts. So this seems like a reasonable thing. So the distance between these two is how long our time constant is. And it's shown down here at the bottom of the screen. So where it says x2 delta 1 is the difference between cursor 2 and cursor 1, which is 291.91 microseconds. So let's go back to our lab sheet thingy. So we figured out what our time constant is. And then based on that time constant above, calculate a value for the capacitor. So we have experimentally determined what the time constant is. We have measured what the resistance is. And because this is an RC circuit, tau is just equal to R times C. So C should just be equal to tau divided by R, right? So we figure out what the time constant is, just doing a little bit of math there. I'll leave that up to you guys. And then now we're asked to notice how changing the frequency of the input signal affects the output. So it suggests 500 hertz, then 1 kilohertz, and then 2 kilohertz. So let's look at that really quickly, and then we'll be done with the lab. So I'm going to go back to the wave gen, and I'm going to increase this to 500 hertz. So what can we see about this picture that's significantly different than the last one? Obviously, stuff's happening faster because we increase the frequency, but that's not really what we're looking for here. So notice that the blue curve never quite hits the peak value of the yellow curve on either the positive cycle or the negative cycle. So at 500 hertz, we're not allowing the capacitor enough time to fully charge or fully discharge, right? If we increase the frequency up to 1 kilohertz, we should see the same problem, but it's very much more pronounced, right? So why could we not use these high frequencies to calculate our time constant? Right, so effectively, because we're not allowing anything to settle, we never know what's truly going on at t is equal to infinity, and that's some information that we need to figure out what's going on. That's done.